Okay, so again, we're going to talk about, we're going to start at the end to show how complex this can be. And I want to talk about why things don't mix. It's easy to understand why things mix because you've been seeing that since you were 2 years old, right? And you kind of got it back then. And now, so let's start with why things don't. And then we're going to go back and do why things do. And I actually swear to God have an in-class demo, and a real one. It's mostly water. Yes, it is mostly water. This is triethylamine in, it's a mixture of triethylamine and water. And so let's, before I show off what exactly is happening there, let me show off the thermo of triethylamine and water. This is a very complex mixture. As you may have noticed, it's quite pointedly obvious that I have it in ice, but anyways, is it one liquid? Right? Right, you're looking for a meniscus or, whatever, little interface. Okay, for YouTubers, hopefully the camera is focusing. If not, well, I'm not going to fix it. I don't care that much. So, okay, so it is mixed. Notice it's cold. That obviously tells you where I'm going with this. Now, let's think about it not mixed. And so A will be, what is A? A will be water. Triethylamine is actually slightly more dense. I might be screwing that up, but anyway. So here's a jumble of A, and here's this interface that we don't see right now for reasons that will be made apparent. I'm trying to do this funky, it's a little bit hard, especially I'm right-handed. Anyway, so here's A and B, and there's an interface because they didn't mix. And now our job is to figure out why didn't they mix. It seems like they should have. Okay, and again, I see that each one is being liquid, meaning that it's all jumbly, and okay, because it's jumbly because it has entropy. It's not a perfect crystal at 0 degrees K. And I'm thinking, well, why didn't it mix, right? It's clearly demixed. A is, that would be water that's floating on top. It has less density, no tricks, all right? There we go. The reason is that if it mixed, now I know that triethylamine's a base, and bases like to be hydrated. I know because when they mix, they get warm. However, in this particular case, trust me, I have to practice drawing this. If the water, so A would be water, if the water wants to go into triethylamine, it might have to do something like this. Sorry, I'm not doing this too well, but anyway, it gets the point across. The A may have to kind of crowd up among itself. Forms like a little micelle, that would be the right word for it. And the B's then conform to the A's like this. Or however, again, this is kind of crazy arbitrary, but it gets the point. In that if A actually truly did mix with B, it might have done it in this way. Now, I see a lot of jumbly here, and I don't see much jumbly there. Now, normally I would say, things normally mix. Why? Because it's like gases having a larger volume. Of course, if I connect a gas in a small volume to a container with a larger volume, of course it's going to flow into it. Why? And that's entropy, right? Because it has a larger volume, that increases its entropy. And so it's wrapped in glass wool, so it's adiabatic, so we don't have to worry about the outside. We don't have to worry about anything. I know that entropically it's going to go into the volume. Now, solutions aren't that different. A wants to swim in B's pool, and B's other compounds pee in it too. But these are amines, but to do so again, the bigger pool says they want to swim together, but they're going to have to do it this way, which is entropically not favored. So bigger pool forms, but you do it in this highly ordered way, that's against. So in this case, this is definitely a negative delta S, delta mix S. That's definitely negative. So let's start looking at the thermo of that. Let's look in, I won't put actually numbers, but just to remind you, we tend to work in a world of kilojoules per mole. And let's talk about water and the amine. The triethylamine, I won't write them out, so this is mole fraction of amine. And I know that, okay, we're going to start at 0. 0 because if they didn't mix, nothing happened, there's nothing to talk about. And what I'm seeing is that delta S is negative, so T delta S looks like this. And again, this is, mix, or whatever. Anyway, all right, so they don't want to mix, and they don't like it. So this ain't going to happen. However, this is what's going on inside, what's going on the outside. Now remember, I said amines like to hydrate with water. And by that, it means they're going to give up, this interaction energy is good, right? I want to, actually the amine would be protonated, right? So it's like, yeah, we're going to like almost bond together. As much as we have to do it in a weird way, we're still going to be able to bond together. And that's going to release heat to the outside, and that's going to create entropy on the outside. Now remember, this is just really crazy, awesome, wonderful, confusing. Nature wants to increase entropy. Nature wants to increase entropy, and it doesn't care how. If you lose entropy, right now, look at this, I'm saying there's no way this is going to happen. Not from here to here. If that's all I'm looking at, no, it doesn't happen. Right? But nature says, but you might release heat in the process, which will increase the entropy of the outside to offset the loss of entropy on the inside. If you can do that, that wins, because nature only goes one way, and it doesn't really care how you do it. Okay, now here's how that would happen. That would be caused by a release of heat. So I'm talking about delta H. Again, we're in a constant temperature, constant pressure world. Constant pressure world, so heat released is delta H, delta mix of H. I won't forget the mixes. Okay, now H minus TS is delta G. And again, I know it's a bit of a pain in the rear, but delta G's, we always like to think positively, but not when it comes to energy. Negative is good. Why did I add these two together if I didn't want them to mix? That's stupid. I want them to mix. I want delta G to be positive. I want them to be negative. So I can see that I can win this battle if the entropy of the outside increases enough, which is caused by a heat release. Notice, however, I can scale this SOV. I can scale that real easy. Now, can I? Now, again, but isn't delta S a function of temperature? Isn't delta H a function of temperature? Yes. But kind of weakly, so compared to this T, right? Entropy changes the natural log, and H is scaled by heat capacities, which actually tend to be kind of small. So let's forget that. Let's let these guys be static, and I'm going to change temperature. And if I increase temperature, this, right now remember, if this overlaps that, delta H becomes positive. Don't let that get confused, right? It's kind of obvious. This minus that is still negative. Minus a negative is a positive. Yeah, whatever. Right, the difference. The difference is negative. That's my point. Sorry. And again, if I increase temperature, then that will no longer be the case. Now you see why I came in with the cold. I came in with the cold because I'm going to let it warm up. Right? So this is going to be true. It's going to take a few minutes. This is going to be true. You're going to see this demix. It's going to take a few minutes because it's, it's got volume. It's got heat capacity, right? Okay, now you're going to see it demix. That's the whole point. It's actually going to turn cloudy as it forms an emulsion, and then I'll let it settle, and then you'll see a double layer come up at the end of class, and I'll put it on the video as well. Okay, now as I try to think deeply about why that is, and I'm not sure if I'm right about this because of the temperature dependence to enthalpy and entropy, but I'm thinking about it this way. All right, so I'm losing entropy on the outside, but I'm gaining it, losing entropy on the inside, I'm gaining it on the outside, and nature only cares about the net. Now, I am warming it in my hand. I see mathematically that if this gets to override that delta G becomes positive and it won't mix. I see that mathematically, but how do I see it in here? What I'm thinking is that if the entropy gain of the outside is what allowed it to happen, the outside is presently, my hand is presently losing entropy. My hand is now cold. My hand has less entropy. The outside, which was so important, is now not so important anymore because it's being diminished because there's a loss, right? So now this net, the thing that carried the day is no longer able to do so because it incurred a loss. It incurred a loss by warming the solution. So, see that? Yeah? Yeah, you see that? We're already at the emulsion stage. If I just settle it for a second, can you kind of see at the bottom? The views of the outside. Maybe if I brought a big one like that candy bar. Okay, so I'm going to leave this for now. All right, so anyway, at the end of the day, this is going to demix. And this is exactly what's going on, and here's the microscopic picture that explains it all. You guys look kind of bored. Is there dress up in a giant chicken costume or something? A's for everyone. I would like to do that. That mean old dean won't let me. Wasn't for that, everyone would have A's. So, okay, now that's as complex as it can get. So you know what? Let's back off. Let's back off and get back to gases. Crawl our way back to solutions, easy solutions. Then include this delta H bit for losing cases, like this case, where the mixing entropy is not positive. And then understand that, which will take about 2 more days. Okay. Now let's go back. Let's go back and think about delta G changes. And to do that, let's actually go back to vapors. So vapors. I don't like how this thing goes. There we go. Okay, vapors. Now I know that dG, and I'm mixing things, so I better make sure I keep my A's and B's separate. And of course, I'm in a world of constant temperature. We've done this. We've done this a while ago. You know this. Okay, in case you forgot, we've done this. Okay, and now again, I'm going to use a vapor equation. I'm going to do that, and therefore, I'm going to integrate. I'm going to integrate the change in G, which is going to go from 0 to G. So that's just kind of a joke. So that's, of course, the change. Sorry, not whatever. Sorry, I misspoke there. Don't worry about it. That's the change in G. And this is going to be the change in NART over P dP. And then I'm going to have an initial pressure and a final pressure. And this is N sub ART, constant temperature world, ln PF over P9. Okay. Now, what I'm going to do, again, these are gases or vapors. How is a gas and a vapor? Are those just 2 words from the exact same thing? The answer is yes, but kind of. Gases are gases, but vapors are gases that came from, you're really going to leave me hanging, huh?
Liquid.
Came from a liquid, right? Right when I'm holding a martini and I smell that, oh yeah. Four Loko, oh you don't know what I'm talking about. Remember, a vapor is a gas from a liquid. Okay, and again, what I'm doing is, I'm actually going to let the liquids mix, but I'm only going to analyze the gases. Again, I got to emphasize this enough. These are the vapors of a liquid mixture mixing themselves. I know it's going to work. I know gases mix. It's rather irrelevant, or so it seems, that these gases came from a liquid that lies underneath. We're not worried about that, right? It doesn't matter so much where they came from. Oh, yes, it does. Regardless, now I know that this is true for gases. We've already done this. I just want to point out that we're going to do a couple things a little different. We basically recognize this. We've already done this, right? We already talked about gases mixing before they reacted. We're not even going to do the reaction part. Okay, this is an aside. F will be the partial pressure of the vapor, not the gases, the vapors. It's kind of important. This will be the partial pressure of A or B, the vapors, after A and B have been mixed together. And now PI, this is where it's going to be a little bit different. Now, when we did this exact same thing before, maybe you forgot, watch the videos before the third test, you will. I look at the YouTube, I see this giant ass. Here's watches time. First test, second test, third test is probably going to. Okay, so when we did this before, we were doing chemical reactions in the gas phase. We had to worry about bonds being broken and made, and we only can figure that out in a crude way from the data tables in the back of the book and Hess's law. And this part was the entropic mixing part. We've done this already. And because I had to throw in a Hess's law component, remember the Hess's law tells you starting and endpoints. The in-between had these correction factors, but because I had a Hess's law component, that guy had to be what? You did it literally a few hours ago. Oh my God, question 4. P0, P0 is 1 bar, right? Wait, sorry, don't write it down, don't write that down. My bad. Before, when we're doing reactions, because we can start out with A and B are going to mix and then react. There's no reason to not have them at 1 bar in the box, and then they'll react whatever. Now, and I have to use 1 bar because I'm also having to include that bond breaking and making, which comes from the data tables in the back of the book, which comes from the Hess's Law thing that you did in high school. So I'm obliged, I have no choice, and it kind of makes sense to have the initial pressure of 1 bar. But not when it comes to a vapor, especially when tables in the numbers from the table in the back of the book, they don't apply. See, this part's actually kind of easier. If that is not the case, the initial pressure will be what's called the pure partial pressure. Let me write that out. Pure partial pressure. Now what that is I have water, and it's true I can smell the water. It's weird how you can smell water, but you know you can. It's polluted. Must be from our drinking fountain. So I know I can smell the water. And this is pure water, and so there is vapor, of course, I can smell it. That's why this will eventually evaporate, right? That's actually an answer to a question on the homework that's coming up. I know that it's going to make some vapor, I can smell it. And of course I know it's not 1 atmosphere of vapor, because if it was, this would be boiling, right? That's actually, by the way, as we get into it, the definition of a boiling liquid is a liquid whose partial pressure is an atmosphere. It makes sense. There's nothing stopping the vapor from just, right? That's when you boil. Okay, so pure partial pressure, in the case of water, by the way, it's about 600 pascals. Notice that's really freaking small, right? Because the partial pressure of air itself, being at 1 bar, is 100,000. Water is around 600, right? That's a pretty big difference, right? 26% roughly. So it kind of makes sense that our initial pressure will be a pure partial pressure because, for one, that's really freaking sensible. Liquids are not boiling all around, and if they were, why am I worried about them mixing? Number 2, I don't need to use 1 bar because I'm not doing chemical reactions, and this is not a correction factor to the number in the table in the back of the book anymore. It just stands on its own. So that's why I'm doing that. And now this is A, let me figure out what the total is. Again, this is the thing I wrote a minute ago. I put it in, I erased it already. I put this in the form of the mixture minus the individual components, the sum of. Forget about that. You're never going to see that again. It's a nice definition, but I don't need it. Let me do it this way. Okay, I'm just writing what I already wrote, and the only difference is partial pressure over the pure partial pressure. Now, the other difference is that G is energy at size extensive, so I can't forget that. The reason I'm doing this is because B has entered the room. Okay, there we go. And, okay. So now what I want to say. I'll keep working down. I kind of painted myself into a corner. It's funny, is I prep for about an hour before class. And if you didn't see it before, right, now that's an emulsion. It's almost demixed. I prepped for an hour before, and I realized that there's kind of a better way to express this than when I wrote my notes, so a little bit of a struggle here. Okay, let me divide by n, because if I divide by n, I've got the chemical potential. Sorry, I wrote that kind of funky, and that means I've got RT. How do I want to do this? Chi A. I'm not going to quite put in, I'm heading for ln chi A. I'm not quite there yet. I'm going to still put this as partial pressures. For a weird reason. I know, we had this before, that the idea that the partial pressure of the vapor in the mixture will go down proportional to its partial volume, meaning that this is chi A, ln chi A. I'm heading there. Hopefully it's very telling. Hopefully it's very telling that, here, let me do it this way. Hopefully it's very telling that I'm not writing that for a good reason. I will, but I'm just not there yet. Because I know this does look like what we had done before. And it should. Okay, so anyway, all right, again, so hopefully we're all okay. This is not hard. I just divided by number of moles to get my change in chemical potential of these vapors. I know that I can smell the vapors. I know that there's vapors here. And later, when I add some ethanol and drink it, I'm having a hell of a day. I know that there are vapors, I can smell them, and I know that their vapors are going to mix. That's obvious, quite obvious. That's what the officer said when he pulled me over. And what? And I know those vapors mix, and this is the change in chemical potential of those vapors mixing. And of course, I will have let it come to equilibrium. It's not quite there yet, but it will. Here's the trick. See, remember, I'm supposed to be talking about liquids. Why am I talking about vapors? What's the chemical potential of vapor water, right? Okay, it's a little out of equilibrium. You like my demo? It's a little out of equilibrium, but let's say it was equilibrium. The chemical potential of the vapors is equal to the chemical potential of the liquid. So if I add some ethanol, and it of course has a little bit of a higher partial pressure, you can tell, you can just smell it, right? And that's why it's a little, you got to be careful of something. That's why some organic liquids are very dangerous, because if they have very high vapor pressure, they're more flammable. All right. I know that when I add ethanol, it's going to have vapor, and its chemical potential will equal that of the ethanol in liquid. And so, if those change on top, do they change the same on bottom? Do they? So remember, this is the change in the chemical potential of the vapors. Now, we already know that the chemical potential of the vapor for water and separately ethanol, those are the same. And when they mix, they're still the same. That's why ethanol doesn't form more vapor. I mean, and it's not doing that because it's at equilibrium. So therefore, is the change in the vapor chemical potential, given that the chemical potentials of each individual are already the same, is therefore their change not the same? You're just thinking about that genetics test, aren't you? That's exactly, okay, look, I know, you're chomping at the bit at this point. Actually, you're doing nothing, which is worse. Okay, so the change in the chemical potential of the liquid is the same as the chemical potential. God, change in the chemical potential of the vapor is the same as the change in the mix of the liquid. So remember, this is the vapor. It's the vapor because that's how I derived it. I didn't put it there. But it's the same as the change in the chemical potential of the liquid. Okay, here's the big point. I am going to take exact thermodynamic things that I know for gases, which we have been busting our ass for 2 months, understanding this stuff, and it's not that bad, and I'm going to take that knowledge and apply it to liquids because I can. The awkwardness is that I'm not analyzing the liquid directly, I'm analyzing the vapor above it. But the gain is I know how to do it. And it doesn't matter. It's just a little awkward. And the way I often put this is, the way we're going to do all of these analysis is, imagine I have a liquid and I have like a mass spec. Imagine I have like a little mass spec probe, and I can just kind of point it over the liquid and measure the partial pressure. That's very doable, because mass specs say, you got this much oxygen, you got this much nitrogen, a little bit of argon, a little bit of CO2, and 600 pascals of water. And then I mix in some ethanol, and then it'll give me the new partial pressure. It will go down, and then it'll say, oh, by the way, I saw some ethanol too. And so now I get that, and so now I've measured the vapors, I plugged it into this equation, but I know exactly the change in the chemical potential of the liquid. If it's negative, what happened? Did it mix? Right. If it's negative, it mixed. Right. G is downhill. And another thing, not to forget, again, I will end a little bit early. What I'll do is to make the reason this is actually always shockingly easy, this chemical potential versus delta G. I know it gets to be a pain in the rear. I will always make everything 1 mole total. So I can talk about delta G, and I often actually get it kind of confused in my notes whether I'm talking about delta G. You've already seen that. So whether I'm talking about delta G or talking about chemical potential, I'm really doing both at the same time because I'm just dividing delta G by the number 1. It just happens to be 1 mole, which turns into a chemical potential. So let's see, is there anything else I really want to say about that? Okay, last bit is before I let us go, so you can get ready for your genetics test, is obviously this is going to simplify. The question is the partial pressure in the mixture equal to this, where this is the mole fraction. You do want to write this down, by the way. I know I'm not using the word, mole fraction in liquid. Okay, now as you can already see, we're going to devolve into that equation that you've already had for gases mixing, for liquids mixing, as long as the partial pressure of the vapor in the mixture, which is how we analyze things, even though we're talking about a liquid, if the partial pressure of the vapor in the liquid mixture is proportional to the mole fraction, not in the vapor. If this was the mole fraction in vapor, this would be perfect. This is the mole fraction in the liquid. If this is the case, then you know that this turns into RT chi A ln chi A plus RT chi B ln chi B, right? You've already had that. You've already done some stuff with that. Okay, now all that has to be is true is that the mole fraction in the liquid is the same as the mole fraction in the vapor. How bad of an approximation does that sound? Does it sound bad? Again, if I have a 1-to-1 mole of ethanol to water, remember that's a huge amount of ethanol, don't drink that. If I have a huge amount of 1-to-1 moles ethanol water, would the vapor pressures of each go down by half? No. Sound reasonable? Well, now remember, I have 600 pascals of vapor, liquid, and this is pure. Now, if I dilute every atom, look, every molecule of water has now a molecule of ethanol right next to it. The vapor pressure, I'm thinking, would go down from 600 to 300, and whatever ethanol does, it goes down by half. What do you think? Bad or good? Huh? So now remember, these things are on a surface, and so here's water, and we form vapors because the water kind of launches off. Now I have water and I have ethanol. So every other water doesn't really form a vapor, right? Does that make sense? So does this sound okay? You're just not responding. Okay, anyway, all right, so we'll in here. Let me just say that, yes, this is a good idea. Practically, it's almost a complete failure. What happens is that solutions actually get warm or cold. It always does one or the other. And that means that the way the vapors form is altered. This is very sensible from my perspective. It turns out from, again, hard stuff. Just to remind you, we're talking about liquid mixtures, and we talked about how there's these XX functions, and we started with volume, which would be the volume of a solution minus the volume that of the sum of the solutions the sum of the volume of the solutions before they were mixed. And again, I would think I would mix 18 mils of water and 18 mils of ethanol, and I ought to get 36 mils of resulting solution. I don't. I'd get a little bit less. I would get actually around, I looked it up, I'd actually get a little bit above 34. And so the excess mils would be a little bit less than 2 mils. And again, that's maybe elementary school me doesn't understand, but high school me does get that kind of makes sense. We also had the same excess entropy, we had excess enthalpy, we had, more importantly, excess Gibbs energy, which actually confused me a little bit. We're not really ever going to use these, by the way, especially because we have a definition for mixing G that we talked about last time. We'll just get into this. What does confuse me a little bit here is that, especially for the energies, why the energy, say, of a solution would be different than the energies of the solutions before mixed confuses me a tad bit, because energy is conserved. Regardless, let's not worry about that. I'm never really going to bring this up again, just to get the idea across. We did have this, let's see, we did talk about the more complex, why do things not mix? Because understanding why things mix is easy, because solutions be like gases. Mixing with another solution is like expanding your volume. And to say that they wouldn't want to mix is be like saying that gases wouldn't want to expand if they could. Of course gases expand. If I hook a balloon next to another container that's under vacuum, it'll expand into it. Of course it will. Even if it wasn't, it would still expand into that next volume. That's entropy for you. But counter to that, again, is that example I gave, and I won't redraw it, of how if things mix, if they have to do so in this very orderly fashion, that may hurt us. And again, look at the drawings I did last time. And what I had done was I had some kind of mole fraction, and I did water and amine, and I said that the delta S, and let's multiply that by temperature, so it's energy, And of course, if they're not mixed, that's 0. We talked about how a loss of entropy would not allow mixing. Now that makes sense, and again, look at the picture I drew before. But a gain of entropy from the outside would result, if this was delta H, sorry, I want to quantify those as mixing. Delta H. All right. Now remember, in a P constant P world, constant P constant T, this guy is the heat given to the outside. Basically, that's its entropy, and so that minus that would result in a that would be a negative delta G. Is that right? That might. Wait, that doesn't. Yeah. Sorry. A smaller number minus. Okay, now I'm confused. A negative number, yeah, sorry, that would be a net negative delta G. Delta mix G, okay. Sorry, I got confused because it's a negative. Negative minus another negative. Got myself confused, sorry. Okay, now we also talked about how if I increase temperature, I gave an example of the means in water, how the way I like to think of that is if I was to take entropy from the outside and put it in, then that thing that drove this negative delta S mixture would be a deal breaker for the deal breaker. So in other words, entropy created on the outside by forming a warm solution, if I took that entropy away by heating the solution, the energy has to come from the outside, then this T delta S would then overwhelm the mixing enthalpy. Again, that overwhelms the entropy gain of the outside, and then you get demixing. Now, here's a question I meant to put on the homework, but I forgot to, and I was going to add it, but I think that's a bad idea. Let me do T delta X mix, delta mix X, S, oh God. Okay, one of those days, yep. Anyway, I thought of this question because it helped kind of cement what's happening here. Again, this guy is a loss of entropy of mixing, so therefore it won't mix. Enthalpy can play tricks. All right, let's not worry about that. Here's a question I think would be a good test question. Let's say that if I force these two, this A and B to mix, and I could know, if I could know that T delta mix S, and let's forget about enthalpy right now, let's just forget that it exists, not play games with it. If I only look at the T delta mix S, and was to force them to mix, I'd say in this region I would not get a mixture, so I don't know how I'd measure it. Let's say I could. Then now, so here's the question, and again, I used to have this on homeworks and tests, and I forgot to put it this time. So you folks tell me, here, again, let's forget enthalpy. Here, let's forget enthalpy. Let's say enthalpy is 0. Let's just put it that way. This would be a solution of A and B that doesn't mix. So I have, say, A on top and B on bottom, because entropy is a net loss. And again, let's say that there's no enthalpy. What do you think happens here? Does it still mix? What have I got? All right, first, do I have, like last time, remember I had that triethylamine water solution, and when it was warmed up, remember that there was a boundary between the two. Look at the video, you can see it. Do I have a boundary? Do I have two phases, two liquid phases? Do I have something floating on top of something else here? Do I? What do you think? Or you just don't want to talk? One of you said yes. Meaning you have two liquid phases? What do you think? No one? Really? No one's going to take that plunge? No, I don't have two liquid phases, or no, you don't want to take the plunge? And you're nodding. Okay, coffee, crack, I don't care what you have to take. Okay, the answer is, and I know it's one of those days, looks like I'm already having one of those days, is that you would actually have two solutions, one on top of the other, and the composition, that here, the idea is that, again, you still have two phases, but they're slightly mixed. And in the, let's say the less dense one's the top one, let's say that this is species A. The top one is composed mostly of liquid A, and that would be the less dense. And the bottom one, the more dense, I'm just making that up, the more dense one would have most, sorry, no, I screwed that up, 0, 1, my bad. The bottom one is mostly A, right? And the top one is mostly B, because there's no Ka. Not zero, but very little. Okay, now this is actually a reality for what you call immiscible solutions like hexane and water. This is reality. They do mix, it's just not very much at all. And so again, you like to look at hexane and water. Well, that's weird, but I do because I'm weird. Occasionally, if you are doing a lot of synthesis like I do for physical chemists, maybe you do a reaction in hexane. The byproducts are water soluble. You get rid of the byproducts by washing with water. And we like to think like, well, the hexane stays on top and the water stays on bottom. It's not really true. There is a partial mixing, it's just not very much. And that's why, again, the synthetic side of me, that might be why you wash away your product when you make something. Anyway, just synthetic chemist problems. Okay, I just wanted to throw that out. But now remember, we're going to walk away from this. Just forget this. I'm just going to wipe it out. We're going to talk about why things mix to begin with, and put some equations to that, which we already did. And just to remind you of what those were, what do I want to say? I want to say we started talking about the vapor. So this is for the vapors. Sorry, I'm not writing very big. Remember that we define vapors as different from gases. Is that vapors are gases that come from liquids that are, right underneath them. And so for vapors mixing, they have to be size extensive. So there's my moles. RT gives me the right units. And I know that the pressures change, which is how I calculate my delta G. And I know that I'm going to start out with a pure vapor pressure. So again, if I'm mixing water with ethanol, and I'm just going to look at the water side at first, that I can smell the water vapor. You can smell dew in the morning. And that would be around 600 pascals. And when I mix it, of course, that vapor pressure will go down. And of course, now I have to remember I mixed it with ethanol. And so you can't forget that it's there. That would be weird. Why would water be more special than ethanol when it's clearly not? And every one of you know that, especially tonight. So that's for the vapors. And again, we've already done this. You've already seen this. And the trick was to do this per mole. So divide by the total number of moles. This is Na plus Nb. You know that. There's not much to this. And now this is the mixing change in chemical potential. My bad. Yeah, I thought I was prepared. Apparently not. And of course, this is still for the vapor, but chemical potentials at equilibrium. And I'm defining this to be at equilibrium means that this is the change in chemical potentials of the liquid. Mix of the, God, what is, I really swear to God, I did prepare before class. It just doesn't look like it is the problem. Okay, again, I've mixed two things. I'm at equilibrium. If you're thinking, oh, what about outside equilibrium? What happens when I just mix them? Oh, go away. All right, that's for grad school. Non-equilibrium things are for grad school. Equilibrium things are for undergrad. You got to do the equilibrium before you do the non-equilibrium. So, again, another way I put this was to say that we hijacked what we know for gases because we spent a huge amount of time deriving things like this, how Gibbs energy gets perturbed from its number in the table at the back of the book. We spent a long time with that. So of course I know that this is for gases. The reason I'm bringing it up at all is that I hijack it for liquids, simply dividing by all that work by the number. I'll be friendly and say we just divide by 1 mole. I just added 1 mole. I just have 1 mole of liquid. And magically, the thermodynamics of the vapor are the same as the liquid. Now, I want to point out also that I have not made any approximations at this point. That's really kind of crucial. So let me point out that, okay, chi A, RT, I wish I put, don't write that down, sorry. Oh God, I definitely need to go to the OCD doctor. Chi LN, okay, now, here's an aside. This is called Raoult's law. The idea, of course, is to figure out a nice handy-dandy, what can I put in there that might be a little bit handy-dandy, a little bit easier than what I've written, because God knows we've already done that. That is to say that the partial pressure of a vapor that is coming from a liquid mixture would be the starting vapor pressure times the mole fraction in that liquid mixture. I can't put this enough. I'm sorry, the liquid, geez, something's really distracting me today. Liquid mix. Okay, and if that's the case, this becomes Ka. And don't forget that I should have factored the RT. That's a little bit stupid. There we go. Finish that up. Okay. Now, that's where we got, I'm still reviewing. Class is shot. The reason that this is a bit of an approximation in that, and before it wasn't. So remember, you've seen that, we've already done this, we even had homework questions on this. But there was a difference. Before, we talked about the composition of the gas as Dalton's law, if I'm not, remember we got a little confused between Dalton's law and Raoult's law before. Dalton's law just says that partial pressures are the mole fraction times the total pressure. Raoult's law basically says no, just look at the liquid, not the vapor. It's easier to look at the liquid because, I know that I had a mole of ethanol. I know I had a mole of water. I know I mixed them together. I know what that is. I don't want to go to the trouble of measuring the vapor pressure of the vapor in the headspace above, my Coke, my Jack Daniels, right? So that's too hard to know. It actually, especially, if we're back in the land of cowhead balloons, right, that actually would really be hard to know. So I'm going to make this approximation, and more idiotically, I'm going to call it a law. And by the way, as I said last time, this approximation is a horrible approximation. So this is really pretty much wrong. It does define something called an ideal solution. And here, I'm going to need a new board. Let's see. Do I want to? All right. Before I get into that, I just want to point out that if I do this, if I use this thing called Raoult's law again, the vapor pressure of a gas in equilibrium with a liquid, and that liquid is mixed, its vapor pressure has gone down by the corresponding composition of the liquid from which it came. That's why it makes sense. And one of the more surprising things about physical reality is this actually doesn't work. Okay, forget it right now, say it does. If it does, I can see already that delta G is going to be negative. I'll reinforce that in a minute, and therefore all solutions mix. As we're going to get into, probably not the end of this lecture, but next Monday, we're going to talk about why this is dead wrong and how we make corrections, and then we're going to see that things don't always mix, but that's coming up later. Let's work in the land of liquid mixtures, in the land of ideal solutions. Okay, again, I want to define ideal solutions as where Raoult's law works. And I have no idea why it's called a law. That's my OCD kicking in. If it's not always true, it's not a law, but we gotta call it that anyway. And it's almost never true, and we still call it a law. Someone needs to be shot. Okay, so now what defines an ideal solution? Okay, what makes Raoult's law works, and again, we're gonna prove this probably not today, is, and we're just gonna stick with A and B. A and B have same size. Sorry for my shorthand. Okay, if they have the same size, therefore, the mixing excess volume is 0. And then there's one last bit, so you can kind of forget this isn't really a criterion. These next things define this Raoult's law that it works. Okay, so A and B have the same size, they have the same interaction. Interaction. Okay, so I like you this much, and the new person is your twin sister. I can't tell the difference. So in that case, the mixing change in internal energy would be 0. I'm forgetting units, but screw that. We aren't worrying about that right now. Okay. This and that means that, which forms an ideal solution. So don't forget that. That's not a big deal. Okay, now, all right, now you've all said you want a little bit more help with tests. What section? Derivation or true and false? True and false. Now, I'm not promising that, all right, but it's kind of clear that this is where I would go. All right, now, that's the definition. What's the consequence? Consequence is quite easy, given that delta H is delta U. And again, we're in a constant pressure world, so the P is going to come out. And I am forgetting all the mixes again, which I should not. Mix. And obviously this is 0. And I ought to be doing this per molar as well, so I'm kind of screwing that up. Let me go ahead, by the way, let me go ahead and put little m's. If you don't write this, or do write this, whatever. I just want to point out that, sorry about this. What I want to do is I want to do everything per molar, because that's how I steal the thermo from the vapor and apply it to the liquid. Is that I make everything per molar. All the G's per molar are chemical potentials. All chemical potentials are equal. Now remember, I get lost in this myself because all I'm doing is dividing by 1 mole. Because I'm just going to mix a mole of water and a mole of ethanol, right? It's kind of a magic trick, but it does work. And I just kind of screw up. I screw up sometimes by forgetting that. Okay, so in that case, here's another consequence. Therefore, delta mix G, again per mole, which is delta mix H per mole, which is already 0, minus T, delta mix S per mole. All right, I've already defined this. And another therefore, delta mix, what is wrong with me? Mix per mole is, I don't know why we, M I get for mole, so why do we use the letter N for mole? I've never understood that. That would be R, Ln chi A. In fact, there's a minus sign, right? Minus sign. And so basically what I'm doing is I'm taking delta G, which is defined above, and I'm just dividing by minus R. And I am screwing up, aren't I? Yeah, I should have a what? I should have a chi A. Right. Yeah, right up there, because there's G per mole. Right. Sorry, I don't know why. I always tend to do that. You even saw me doing the homework. Not that there's anything wrong with the derivation, I just keep forgetting it. Minus R chi B, ln chi B. And it would be a lot neater if I just factored out a minus R, but I didn't. So that was a little stupid of me. Okay, all right, so now there's another way to do this, by the way, and maybe don't write this down. Here's one way to prove it. Again, as long as I set that equal to 0, which is, now let's back up just again for a second, because I had you work a homework question on this. Now, I was alluding to this very moment. I had mixed A and B together, water, ethanol, or whatever, it doesn't matter. And they did mix. And I'm holding the cup, a glass cup. Is it hot or cold? Now again, imagine you picked anything out of the kitchen cabinet, bottom kitchen cabinet, right under the sink. And you know there's lots of stuff in there. And I mix them together. Does it get hot or cold? Generally kind of hot, right? Yeah, things get hot or cold, but in this case, for ideal solutions, right, nothing happens, right? You've already had a homework. Now, I can tell you, my parents, I think, I grew up very poor, but my parents, I think, did, they were pretty good, but occasionally they let us, like all parents do things that were, I can't believe I'm alive, let's put it that way. My parents, when I was a little kid, me and my brother, we wanted to play chemistry set, so my mom literally let us get all the chemicals underneath the kitchen sink and mix them together. I reminded my mother that once at the beach she let me and my brother dig a tunnel in the sand. A lot of kids get killed that way. If you have kids, do not let them dig a tunnel in the sand, all right? Don't drink salt water either. I'm full of good advice. So reality is, again, when most things mix, anything, just about anything mix, you will actually feel it gets slightly warm or slightly cold. That's almost always true. And cold packs, right? For those of you who were in sports or whatever, injured your ankle, cold packs, when you break them, their solution's mixing, they get cold. So this, again, my point being, this is really not true. And it's not true in kind of a big way. But right now we're saying they're true. All right, now here.